We want to sketch the graph of f of x equal to x minus 2 divided by x plus 1. To sketch this graph, we're going to go through our 7-step process here of gathering information that we need to help us create the graph. We're going to begin by finding any intercepts. To find x-intercepts, we set the function equal to 0. So here we want to set the numerator equal to 0. So we're setting x minus 2 equal to 0. Solving for x, we get x equal to 2. Therefore, we have one x-intercept, and it is the point 2, 0. Next, to find our y-intercept, we plug 0 in for x. So we're taking f of 0. So we have 0 minus 2 divided by 0 plus 1, which simplifies to a negative 2. So our y-intercept then is the point 0, negative 2. Next, we want to find any asymptotes. We'll start with vertical asymptotes. In order to find those, we first try to simplify the function by factoring if it needs to factor. This function is already simplified. Therefore, the next step then is to set the denominator equal to 0. So here we are setting x plus 1 equal to 0 and simplifying. So we get x equal negative 1 as our vertical asymptote. For the horizontal asymptote, we look at the degree of the numerator and the degree of the denominator, and we compare those. Here in this case, the degree of the numerator is 1, and the degree of the denominator is also 1. Since the degree of the numerator equals the degree of the denominator, then we look at the leading coefficients of both the numerator and denominator, and we take the ratio of those leading coefficients. The leading coefficient of the numerator is 1, and the leading coefficient of the denominator is also 1. So the ratio of 1 over 1 gives us our horizontal asymptote. So in this case, y equal 1 is our horizontal asymptote. Next, we want to find the first and second derivatives. So our original function is a quotient. We have both a numerator and denominator, so we're going to have to use the quotient rule to find the derivative. So f prime of x is going to look like, we begin by taking the denominator, which is x plus 1, times the derivative of the numerator, which is 1, minus, now we have the numerator, which is x minus 2, times the derivative of the denominator, which is 1. And then that's all divided by the denominator squared. So x plus 1 squared. Now when we go to simplify this, our x's drop out, and we're left with a 3 in the numerator, and then we still have an x plus 1 squared on the denominator. Now, since we have to take the second derivative, I'm going to rewrite the first derivative by bringing the denominator up to the numerator and making the exponent a negative. So we're going to have 3 times x plus 1 to the negative 2. This will allow me to use the power rule to find the second derivative. So now f double prime of x is going to look like, bringing the negative 2 out in front, we're going to have a negative 6 times x plus 1, and then subtract 1 from the exponent. So our second derivative then looks like a negative 6 divided by an x plus 1 cubed. Now the domain of f, f prime, and f double prime is all the same. If we look at the denominators in all three of those functions, when x is equal to a negative 1, it creates a 0 in the denominator. So our domain then is going to be all x values such that x is not a negative 1. So all x such that x is not equal to a negative 1. Next, to find the critical values of the function, we look at where the derivative is equal to 0, and we also look at when the derivative for x values at which the derivative does not exist. So I'll begin by setting the first derivative equal to 0. So we are setting 3 divided by x plus 1 squared equal to 0. Well, since the numerator is a constant, the first derivative is never equal to 0, so there is no solution to this. The first derivative is never equal to 0. Now when we think about the x values for which the first derivative does not exist, it does not exist at x equal -1. However, x equal to -1 is not in the domain of our function f. Therefore, there are no critical values. Next, we want to find any relative extrema and the intervals of increasing and decreasing. So relative extrema are relative maxes and relative mins. Since there are no critical values, that means that there are no relative extrema, because any relative max or mins occur at critical values. So in order to find intervals of increasing or decreasing, we will use our vertical asymptote, x equal -1. So we will divide our number line up at -1 to create two intervals on the x-axis. And we will pick test values in these intervals and test these values in our first derivative to determine whether they are positive or negative. And that'll tell us whether we're increasing on that interval or decreasing. Remember, if the first derivative is positive, we are increasing. If the first derivative is negative, then that means the function is decreasing on that interval. So in the interval -infinity to -1, I can choose a test value. For example, I could choose a -2. If I plug a -2 in the first derivative, f prime of a -2 turns out to be a positive value. It is greater than 0. So since the first derivative is positive, this tells us that we are increasing on the interval -infinity to -1. Next, let's choose a test value between -1 to infinity. So for example, I could choose 0. If I plug 0 into the first derivative, f prime of 0 turns out to be a positive value. So that means we are increasing on the interval -1 to infinity. So now we have our intervals of increasing, and it turns out that our function is not decreasing at all. It's only increasing. Next, we want to find our candidates for possible inflection points. We find those by setting the second derivative equal to 0. So we want to know when is f double prime of x equal to 0. So we are setting a -6 divided by x plus 1 cubed equal to 0. Well, since the numerator is a constant, it is never equal to 0. So there is no solution here. So there are no candidates for inflection points created by setting the second derivative equal to 0. We can also have possible inflection points by looking at where the second derivative does not exist. The second derivative does not exist at x equal -1, but x equal -1 is not in the domain of our original function f. Therefore, we have no inflection points. Next, we want to determine concavity, meaning we want to find the intervals in which the function is concave up and also find the intervals in which the function is concave down. And to do this, we typically use our inflection points. However, in this case, there are no inflection points. So instead, we will use our vertical asymptote, x equal -1, and divide the number line up around our vertical asymptote. So we're dividing the x-axis into two intervals from -infinity to -1 and then -1 to infinity. We already know that our function is increasing on both of these intervals. Next, we want to determine concavity by using our second derivative. So I can pick a test value out of the interval -infinity to -1. For example, I could choose, say, a -2. If I choose a -2, plugging -2 into our second derivative, f double prime of -2 turns out to be a positive value. It is greater than 0. So this tells us, since the second derivative is positive, that we are concave up on this interval. Next, we want to determine whether we're concave up or concave down from -1 to infinity. So let's pick a test value in that interval. For example, I could choose a 0. If I plug 0 into the second derivative, f double prime of 0 turns out to be negative. so the second derivative is negative. This means that we are concave down. Since the second derivative is negative, we are concave down on the interval -1 to infinity. Next, we're going to use all this information we've gathered in A through G to graph our function. I'm going to begin by graphing our intercepts. So we had an x-intercept of 2, 0 and a y-intercept of 0, -2. Next, I want to graph our asymptotes. We had a vertical asymptote at x = -1 and a horizontal asymptote at y = 1. We found that there were no critical values, so there were no relative extrema, so there are no relative maxes or relative mins. We also know that the function is increasing on both -infinity to -1, and it's also increasing from -1 to infinity. On the left side of the vertical asymptote, we know that we are concave up. I'm going to pick a couple x values to the left of the vertical asymptote to help in graphing that. For example, I could choose, say, a -2 and a -4. If I plug a -2 into f of x, we get 4. And if I plug a -4 into our function, we get f of x equal to 2. So there's a couple additional points. So these points help us in graphing the function on the left of the vertical asymptote, keeping in mind that the function is increasing and it is also concave up. Next, I'm going to graph the right-hand side of the function, the right hand meaning right side of the vertical asymptote. We've got a couple points already plotted, and those are our intercepts. I'm going to pick a couple more x values, though, to get a couple more points on here. For example, if I choose 1 as an x value, if I plug 1 into our function, we get an output of -1/2. And if I choose 5 for x, we get a function value of +1/2. So I'll plot those as additional points on our function. Now I can connect these 4 points, keeping in mind that our function is increasing and it is also concave down. So there's our graph of our rational function. One of the things that you can do is plug the original function f of x into your graphing calculator and graph it to check your answer. And I encourage you to do this. One thing I do want to point out, though, that is in your graphing calculator, oftentimes it'll graph the vertical asymptotes as vertical lines. And I want to remind you that vertical asymptotes are not actually part of the graph. We often draw the dotted lines to help us see where those asymptotes exist.